In this example, we are going to use the equation generated by the polar coordinate to solve the problem. There is a ball pushed by the rod in the slot here. Initially, the angle is equal to 0 degree, and then after some time, it moves to angle equal to 30 degree. The motion of the rod is due to the angular velocity, which is given by 0.8 radian per second. You are going to find the acceleration and velocity of the ball at this moment. To find the kinematic parameters of the ball here, first of all, we assign the polar coordinate on this system, where you have the origin here. The distance from the origin to the ball is called the radius r. Er is the unit vector for the radial direction, which is moving from point O to the ball. E theta is the unit vector for the transverse direction, which is always 90 degrees to the radial direction. The magnitude r is not given in this case. However, from the triangle relationship here, r cos angle is equal to 0.2. Rearrange the formula, you obtain the r equal to 0.2 divided by cos angle, and 1 over cos angle gives you the second. So substitute the r inside this formula, you obtain the displacement vector, and to find the velocity vector in the radial direction, you have the velocity equal to the sliding velocity, which is the dr over dt. So when you take dr over dt, you found that your r is in angle. To differentiate with the angle, then you multiply with d angle divided by d angle here. Then we can switch the d angle and dt here. So you know that d angle divided by dt is the angular velocity. Then you can substitute 0.8 inside. And differentiate 0.2 second angle, you obtain the secant. So don't forget your constant, 0.2, multiply with 0.8. So this is the r dot. So you success to obtain the radial velocity from here. Let's continue with the transverse velocity. So transverse velocity is r, which can be obtained from here, multiply with the angular velocity, which is 0.8. So after substitute and compute it, you obtain this velocity. Let's continue with the acceleration. So you need to compute the r double dot, which is the sliding acceleration. To obtain the sliding acceleration, you need to differentiate r dot with respect to time, d over dt. Before we continue, it's important to highlight that the rod is moving in a constant angular velocity. Therefore, the angular acceleration is equal to 0 in this case. This is the r dot that we obtained previously, and we need to differentiate it again to obtain the sliding acceleration r double dot. If the angular velocity is not a constant, then you need to differentiate the r dot by using this approach. First of all, let us differentiate the secant, and then you constant the tangent and angular velocity. So this part is constant, and then you differentiate secant. Then you continue differentiate tangent, and take the secant and angular velocity to be constant. Lastly, you differentiate the angular velocity, and you take the secant tangent to be constant. So with that, you obtain the differentiation result. You can't differentiate the function in angle with respect to time directly. To differentiate the function with respect to the angle here, then you need to multiply d angle divided by dt, where these two terms can be cancelled and you get back the original function. Then you can perform the differentiation for the secant. You obtain the secant. So this is the angular velocity, and then you continue differentiate this term. So you cannot differentiate directly, you need to differentiate with respect to angle. Then you need to multiply with the d angle divided by dt. So differentiation of the tangent angle gives you the secant square angle. Lastly, for this part, you obtain the angular acceleration. Since our angular velocity is equal to 0.8, which is constant in this case, therefore we can simplify the differentiation. So we can substitute the angular velocity to be 0.8, and 0.8 multiplied with 0.2 here, you obtain 0.16. So if you differentiate the sliding velocity with respect to time, so you need to differentiate the second first, which is this, and then take the tangent to be constant. So the angle dot here is no longer exists because you multiply with the constant here to obtain 0.16. Then you continue with the second component where you differentiate the tangent to obtain this, and then you take the second to be constant. So again, this part is no longer exists because we already consider it in the constant here. Lastly, this part is not exist because you only differentiate with two terms here, which is the second and tangent. This is true because when you compute this in the previous formulation, you have to multiply with the alpha. Since the angular velocity is constant, your alpha is 0. So this part eventually will be equal to 0. With that, you success to obtain the sliding acceleration to be this answer. Since we want to obtain the velocity and acceleration in angle equal to 30 degrees, therefore substitute the 30 degrees inside these two formulas, you obtain this answer. So far we obtained the answer for the R dot and R double dot to be this. When you substitute angle equal to 30 into the formula for R, you obtain the radius equal to 0.2309. So substitute it inside this formula and multiply with 0.8, you obtain 0.1848. Substitute the R to this and then multiply with 0.8 square, then you obtain the normal acceleration or the centripetal acceleration, which is moving toward the center. Then you should obtain 0.1478. When you minus it with the R double dot, you obtain the radial acceleration, which is equal to 0.0985. Since the result is in positive, therefore the direction for the radial acceleration will be in the positive radial direction. When you substitute the R dot to this formula and your angular velocity is equal to 0.8, multiply it, you should obtain this answer. So this is the Coriolis acceleration. Lastly, since the angular acceleration is 0 here, after you substitute inside, you obtain the tangential acceleration to be 0. So this part can be cancelled. Then we obtain the transverse acceleration to be in this direction, and the magnitude is equal to 0.1707. So if you substitute all the value that you obtain for the velocity and acceleration, then you can plot the velocity diagram and acceleration diagram here. So in the radial direction, so you have the ball here. So the resultant velocity can be obtained from the radial direction and transverse direction by using this formula. So this is the magnitude. And for the acceleration, this is the radial acceleration and this is the transverse acceleration. And you can find the resultant by using this formula. With that, we success to obtain the velocity and acceleration of the ball at angle equal to 30. You can also find the direction of the velocity and acceleration by using the arctangent of the velocity in the transverse direction divided by the velocity in the radial direction. So this angle is the angle here. When you calculate this, you obtain 60 degrees. So over here, the angle is 60 degrees. And you know that from this reference line to this radial direction, the angle is 30 degrees. Therefore, over here, you have 30 degrees. 30 degrees plus 60 degrees So the resultant velocity is acting at 90 degrees away from the reference line. With that, the resultant velocity can be found in this direction, and the resultant velocity is always tangent to the path. You can also find the direction of the acceleration, which is here, by using the same approach. By taking the arctangent of the transverse acceleration, which is this, divided by the radial acceleration, which is this, then you should obtain 60 degrees. So this angle is 60 degrees. So same as previous problem, we have 30 degrees away from the reference line here. Therefore over here is 30. So the resultant acceleration is acting at 60 degrees plus 30, which is 90 degrees. So you see in this case, we have the resultant acceleration acting in the same direction with the resultant velocity. If you want to find the travel distance from the initial point to the point here at angle equal to 30 degrees, so we can use the triangle relationship here, where previously you obtained the radius at 30 degrees is equal to 0.2309. So by taking 0.2309 sine angle, you obtain the travel distance. So when you compute, this distance is equal to this answer. Let's try with more example here. You have a mass B which can slide in the OA arm here. The angle is count from here, where the function is given by this formula. So at t equal to 0, when you substitute, your angle start from 0, which is initially here. Then at t equal to 1, substitute inside, you obtain the angle to be some value. So you see the thing start to rotate in this direction. So differentiate the angle function d angle with respect to time. Then you obtain the angular velocity, and you differentiate again the angular velocity with respect to time. Then you obtain the angular acceleration. The distance between the point O and point B is given by r with the function 0.2 plus 0.04 t squared. So when you substitute t equal to 0, you obtain the r equal to 0.2. So in the initial position, your mass B, let's say, is here. So after some time, let's say t equal to 1, substitute inside, you obtain 0.2 plus 0.04, which is 0.24. So at next second, let's say at here t equal to 1, your radius change to 0.24. So the radius change over the time, and you can measure the sliding velocity by differentiate dr divided by dt. Then you obtain the r dot. Then you differentiate again with respect to time. So you obtain the d squared r over dt squared. So this is the sliding acceleration. You should know that this is the radial direction, where the mass B is slide in this direction. And the direction tangent to the radial direction is called the transverse direction. Next, we are going to find at t equal to 3 seconds, what is the magnitude of the velocity and acceleration of this slider B. At t equal to 3 seconds, substitute inside this formula, you obtain the angle is equal to 65.3 degrees. So this is your radial direction, and this is your transverse direction. In the radial direction, you have the radial velocity, which can be computed by using this formula, r dot. So you substitute t equal to 3 inside the r dot, then you obtain the radial velocity to be 0.24. And in the transverse direction, you have this velocity to be r theta dot. So substitute the r inside this formula and angular velocity inside this formula, and compute it at t equal to 3, then you get the answer to be 0.414. Take the square root of the Vr square plus the V theta square, Then you can find the magnitude of this velocity. For the acceleration, you have the radial direction here and transverse direction here. So for the radial direction, to compute the radial acceleration, you need to compute the sliding acceleration from here, and then you can compute the centripetal acceleration by using R, which is this. So substitute t equal to 3 inside this formula and multiply with the theta dot. So this is your theta dot, substitute t inside here and take the square. So after you compute, you obtain the result in negative. So it means it's opposite to the radial direction, which is in this direction. Then you continue to compute the transverse acceleration by using this formula. And for the first component, you have the Coriolis acceleration, where you need the R dot, which can be found from here, and theta dot can be found from here. Then you can continue to compute the tangential acceleration, R theta double dot, where it can be found from here. After calculation, you should obtain the transverse acceleration to be this answer. And then to find the resultant acceleration, you take the square root of the transverse acceleration square plus the radial acceleration square. So with that, you should obtain this magnitude. You can refer to this for the detailed calculation.